In this video, we're going to prove that every finite extension of a field is an algebraic extension. So I've written the theorem statement here. Let F be a field, and let E be a finite extension, that is, one having finite dimension as a vector space over F. We'll prove that E is an algebraic extension of F, that is, every element of E is algebraic. So here we go. Here's the proof. Let's start in blue here. All right, suppose A belongs to E. We will show A is algebraic over F. And the approach that we're going to take here is we're going to use the fact that E has finite dimension as a vector space over F. That's going to be the key approach here. So one thing that we know, let's let N equal the degree of E over F. Okay, then N is the dimension of E as a vector space over F. We're going to use that here. Okay, so then one thing that we know is the set 1, A squared, up to A to the N. This has N plus 1 elements, so it must be linearly dependent over F. Okay, let's think about why that is. Well, if I have a set that has N plus 1 elements, I know that there is a basis for E over F that has N elements, and that set is going to span E over F. One thing that we know is that we have a theorem that you can't have a linearly independent set that is bigger than a spanning set. So if this set has N plus 1 elements, it's going to have to be linearly dependent over F. And at this point, I might advise you to just go ahead and stop the video and see if you can finish the proof on your own. Once you have this, you have enough to prove that A is algebraic over F. So pause the video and see if you can see what I mean. If not, then feel free to continue watching. All right, I'm going to move on. Okay, so because this set is linearly dependent over F, that must mean there exist elements C0, C1, up through Cn belonging to F. And let's say they're not all zero. Not all 0, that should be a comma, not a semicolon, such that C0 times 1 plus C1 times A plus C2 times A squared, etc., up through Cn A to the N is equal to 0. Okay, that's just stating what it means for this set here to be linearly dependent. That's one interpretation, is that there's a non-trivial linear combination over F that gives 0 of those elements. Okay, so there exists some C0, C1 up through Cn coefficients such that this is equal to 0. Okay, but then this polynomial, C0 plus C1x plus C2x squared, etc., up through Cn x to the n, this is a polynomial in f adjoint x of degree less than or equal to n. Less than or equal to, because we don't know whether Cn is 0 or non-zero. It may be 0, in which case the degree would be less than n. But most importantly, this polynomial is non-zero, and it has A as a root. And then once we have that, we have a non-zero polynomial in f adjoint x having A as a root. That means A is algebraic over F. Yay. And that means that we're done with this proof, because all we needed to show is that every element A of the extension E is algebraic over F. Now we've proven that. It's kind of magical, actually, how that works. Just using a little bit of what we know from linear algebra, we're able to prove that every element of this finite extension has to be algebraic. But I didn't want to stop there. This is the proof of the theorem, and we're done with that. But I wanted to go a little bit further and show a practical example of this idea in action. So let's do that now. All right, so I wanted to do an example where it's not obvious how you would use other techniques to show that an element's algebraic over the rationals. So I'm going to start with Q as my base field. And for our extension, let's take E equals, so that was F, let's take E equals Q adjoin the cube root of 2. Okay, so that's the set of all A plus B cube root of 2 plus C cube root of 2 squared, which can be written as cube root of 4, such that A, B, and C are rationals. So that's going to be our starting point here. All right, now one thing that we know about this extension field, this has degree 3 over Q. One way to see that is to believe this characterization of elements of Q adjoin cube root of 2, that is, believe my claim that every element is expressible as rational plus rational times cube root of 2 plus rational times cube root of 4. Note that the cube root of 4 is the cube root of 2 squared, that's why that's there. You could believe that, or if you didn't want to take my word for it, you could use one of those theorems that we've proven previously that says if we adjoin a root of a polynomial, of an irreducible polynomial, in this case x cubed minus 2, and that polynomial has degree 3, then the extension by this root will have degree 3 over the base field. So we should have, in either case, we should have an extension of degree 3 over the rationals, which means that as a linear space or vector space over the rationals, it has dimension 3. Okay, and I thought about giving some example like A equals, I don't know, cube root of 2 plus 7. And say, let's prove that that's algebraic. But that's kind of boring. I mean, we could say, well, let's let x equal the cube root of 2 plus 7. And then move the 7 over, x minus 7 equals cube root of 2. And then cube both sides to get x cubed minus 21x squared plus, this was quite a chore I gave myself, 7 squared is 49, times 3, that would be 147x minus 49 equals 2. Move the 2 over, and then you get a polynomial that has cube root of 2 plus 7 as a root. That's boring. Okay, so let's try something harder. Let's try instead showing that A equals the cube root of 2 plus the cube root of 4 is algebraic. Now, truth be told, you could probably use a technique similar to this. It's just going to be a lot messier in this case because now you've got 2 cube roots in play, and they're being added together. So I wanted to show how, in practical reality, you might work this out, that is, prove that this is algebraic just using linear algebra. All right, so the way that the proof goes is first the proof says that this set, 1a, a squared, a cubed, this set is linearly dependent. And we know that that's going to be true because this element here, this is a member of Q adjoin cube root of 2. And that entire field extension has dimension 3 over the rationals. So this has to be linearly dependent. But the trick to actually finding a polynomial for which this is a root is to find that linear dependency. And that's a computational matter. So let's work out what that is. So 1 is equal to 1. I'm just going to express each of these elements, 1a, a squared, a cubed, as an element in canonical form for this field. Canonical form means it's in this form right here. All right, so that's the first element. What about a? Well, a is just cube root of 2 plus cube root of 4. And I'm writing it like this because I know that a basis for this vector space, Q adjoining the cube root of 2, is going to be 1 cube root of 2 cube root of 4. So I'm just organizing everything here so that it follows that format, so that I have coefficients for 3 basis elements. All right, a squared, a little bit more of a pain, but let's see if we can work that out. Cube root of 2 squared, or sorry, cube root of 2 plus cube root of 4 squared, that's going to be cube root of 4, I'm just squaring that first term, and then I've got 2 cube root of 8, that's nice, plus cube root of 16, that takes a little bit of work. So I've got cube root of 4 plus, 2 times cube root of 8, I know what that is, that's 4, plus cube root of 16, I can pull out a cube root of 8, that's 2 cube root of 2. All right, so putting that in my little canonical form over here, I have 4 plus 2 cube root of 2 plus cube root of 4. Now, it's likely at this point that I don't have a dependency quite yet. In fact, I know that I won't because this element here has the same coefficient on cube root of 2 and cube root of 4, and this one doesn't. So I don't think there's going to be any way of getting back to 0 without making both of these have coefficient 0. But if I pull in a cubed, I think that I will have a dependency among these 4 elements. All right, so cube root of 2 plus cube root of 4 cubed. that's going to be equal to the first term cubed, which is 2, plus 3 times the cube root of 4, that's the first term squared, times the cube root of 4, plus 3 times the cube root of 2, times the cube root of 16, that was the second term squared, plus the cube root of 4 cubed, that's 4. So it's going to be 6 plus 3 times the cube root of 16. I already worked out that that would be, the cube root of 16 is 2 cube root of 2, so that's 6 cube root of 2. And I've got the cube root of 32, that's a little bit trickier. I think that's going to be 6 cube root of 4. And I think that that's it. Okay, so cube root of 2 plus cube root of 4 cubed, that's 6, plus 6 cube root of 2, plus 6 cube root of 4. Okay, now do I have a dependency among 1, a squared, and a cubed? And actually, mercifully, I think that I do, and it's not too hard. I think that I have a cubed equals 6 plus 6a. Check that I'm right about that. I think that I am. So that would mean that a is a root of x cubed minus 6x minus 6. And because I wanted to be sure before I spent an hour rendering this video on my computer, I did check using Wolfram Alpha. That is in fact true, that a root of x cubed minus 6x minus 6 is the cube root of 2 plus the cube root of 4. So that was awesome. I'm awesome. We're awesome. Okay, so one thing I want to show you is that there's a little more of a practical way of interpreting all of this, because we're really doing linear algebra here. So what we're doing is we're setting up a matrix, and this matrix, the rows correspond to the 3 basis vectors, 1, cube root of 2, and cube root of 4. Okay, so that 1 in our set, I'm going to write down 1a squared, and a cubed here. That 1 was equal to 1, 0, 0 in terms of our basis. A was equal to 0, 1, 1. I'm just going to put regular ones here. And then a squared was 4, 2, 1 in terms of our basis. A cubed was 6, 6, 6. That was totally unintentional, by the way. Okay, but anyway, what we're trying to do is we're trying to show this matrix has a non-trivial null space which, from the point of view of someone who already knows linear algebra, we already know that this has a non-trivial null space, because having a trivial null space corresponds to being or representing a one-to-one function, and this matrix here represents a function from Q4, that is the set of 4-dimensional vectors over the rationals, to Q3. And you just can't have a one-to-one function from Q4 to Q3, at least not a one-to-one linear function. So we know that this already has a non-trivial null space, but here in this example, what we were really doing was finding it. And that's a computational matter. That's something that you could do with a computer, as long as your computer understands that it's trying to do this over the rationals and not over the reals, which is not too hard. So anyway, what we see here is a way of manufacturing a polynomial that has a certain element as a root, in this case cube root of 2 plus cube root of 4. By the way, no guarantee that this is going to be the minimal polynomial, or that it's irreducible, although in this case this is irreducible, and I'll let you figure out why. But in any case, we will get a polynomial over Q, or in general over our base field, having the desired element as a root. And we did that entirely using linear algebra. Pretty cool if you ask me.